Hello everyone, this is Mark. I'm a doctoral student at the Block Research Group in ETH Zürich and a research fellow at the Imperial College London under the chair of machine learning and pattern recognition. Today I'll talk about experiments we conducted at the beginning of last year to apply graph convolution network to model funicular reticulated shell designs. We often attribute the light-weighted efficiency of funicular shell structures to their expressive doubly curved geometry based on force flow. Just as important, however, is the design of the structural pattern used for form finding, because each pattern prescribes its own feasible geometry design space that can be discovered. With the popularization of computational design methods, researchers have contributed a growing repertoire of methods that vastly reduce the complexity involved in structural pattern design, allowing designers to intuitively and tractably explore and develop patterns with respect to performance goals. The adoption of AI or machine learning has further provided designers an additional arsenal of design methods, allowing the learning of performance-informed guidance to support the design process. But in spite of all these advances, our ability to dynamically traverse a trans-topological design space and gain quick performance feedback and insight is still quite restricted. A key limitation is how structural designs are generally modeled or characterized. We can see that in the trans-topological design space, any two designs will likely to be differently sized, with variable connectivity and therefore no comparable ordering of elements. This means that the nice familiar vector-based approaches we conventionally rely on for modeling, characterizing, and comparing designs are generally not applicable. To get around this problem, designers typically resort to manually engineering their own vector spaces to serve as a proxy for the trans-topological design space they are modeling. Using the design variables characterizing the custom design pipelines, or a selection of statistics describing the design performances, we were representing the designs with techniques like reparametrization or interpolation. These approaches have a number of disadvantages. Chiefly, they are less expressive and can have less approximation power. And many approaches are not able to offer fine-grained predictions on characteristics of individual elements within a discrete system. And this research is motivated to address these modeling challenges, applying a class of machine learning methods called geometric message passing or geometric deep learning to learn performance insights directly from the discrete data structure describing equilibrium shell structures. The experiments are designed to support the computational design process for shell structures. Providing approximation models on 4 subtasks involved are broadly supportive of the design process. We hope to demonstrate the method's feasibility and develop techniques useful for the modeling of shell designs, encompassing variable boundary conditions and topologies. And in today's presentation, we'll use one case study to highlight the research methodology and framework, developing an inverse model to predict parameters to be assigned to an existing pattern according to a structural design goal. Specifically, we will revisit the classic problem of best-fit first network optimization. The goal is to compute the edge force density that may be used to form fine an input structural pattern into an equilibrated shell with a geometry that is as close as possible to a target geometry and maintains a horizontal projection of the initial pattern. A simple trans-topological design space was constructed to create the dataset needed to build the paper's models, consisting of patterns generated with a Python library called CompaSingular within square-shaped boundary featuring random placement of point features. Each size may have a percentage of the nodes left unsupported, creating designs with variable support conditions. The patterns are relaxed before they are form-found using first network analysis. For this case study, the model inputs, which include the input pattern and the target geometry, are described together as features of the pattern's node. This includes each of the pattern's nodes' coordinate position in XY, whether they are supported or on boundary. The target geometry is in turn described as the projected height of the pattern's node to the target surface geometry, and of course the model's output force density, which are expressed as edge attributes. Like most geometric ML approaches, the underlying models are all based on artificial neural networks, which learns to transform the data input layer by layer into the output that we're trying to predict using a set of weights that are learned by the training process. Adapted for geometric learning, each set of features assigned to a design node or edge can be essentially regarded as a data point. Within each layer, each node aggregates features from its neighbors, so that it learns to process and transform the data in a way that is aware of its local connectivity. And by repeating this over several layers, the successive remapping of the data features eventually considers the entire design. This mechanism is called message passing and is fundamental to geometric approaches. In the network's final layer, the mechanism is extended to allow each edge to transform and aggregate data from the bounding nodes in order to obtain prediction of edges' force densities. In the paper, you'll find additional details on techniques we've tried. This slide shows some of the selected design results. Drawn in blue are 4 initial patterns with the nodes projected to the target geometries. The patterns are used as inputs for the trained model, which in turn predicts the edge's force density. Drawn in red are the design freeform found using the predicted force density. We can see that in our basic design space, a reasonable level of accuracy is achieved. As a test, we also compared the performance of the geometric approaches with 2 conventional neural networks using fully connected and fully convolutional networks, which respectively represent the target geometry as vectors of node's height or as a pixelated height field. Although the models are not directly comparable, we found compelling support for the geometric approach as it outperforms the image or vector-based models both in terms of the training efficiency and the final accuracy achievable by several orders of magnitudes. Our presentation today only discusses 1 experiment we've conducted, but you'll find details on 3 additional mappings we've tested in our paper, including a model approximating the form-finding algorithm and a model providing approximate finite element analysis results to provide feedback on the stiffness behavior. The research presented today consists of preliminary investigations that we've conducted at the beginning of last year, and there remains significant room of improvement. First of all, we have to diversify the trans-topological structural design space. Ongoing research also indicates that more advanced model architectures are required to support the modeling of an expanded design space. Work also needs to be done to improve the robustness of the models to handle design inputs that are not close to an equilibrium solution. More rigorous benchmarking of the model accuracies and sensitivities are also needed. In conclusion, we presented today a novel application of a topology-facilitated machine learning approach based on geometric deep learning to learn directly from reticulated shell structure based on funicular form finding. We demonstrated its feasibilities and developed techniques for improved learning in the paper. We provided modeling studies that variously support design exploration, encompassing variable boundary conditions and topologies. Our initial findings provide a compelling demonstration on the opportunities for geometric deep learning to augment the performance-informed traversal of a trans-topological structural design space. Thank you.